Direct volume rendering with a fixed step size works well for scenes with a smooth transfer function, but as the peaks get more and more narrow, artifacts occur. These are especially distracting during motion. To reduce the artifacts, the step size has to be reduced, which drastically increases the computation time. We propose a ray splitting algorithm that can render scenes with arbitrary transfer functions at a controlled precision. But do we even need such high-frequent transfer functions? Now we switch to isosurfaces. Regular semi-transparent isosurfaces can separate the features but cannot convey small uncertainties in the voxel densities. We argue that DVR might be more faithful to the underlying data, as regions with similar densities still contribute to the output. However, smooth transfer functions lead to a loss of small details. A sharper, narrow transfer function is needed. Here is a direct comparison between DVR and multiple isosurfaces. The mathematical model behind direct volume rendering is the volume rendering integral. Let tau be the absorption along the ray and let c be the color along the ray. The output color is then given by this nested integral. In the general case, no analytic solution is known. Our method allows for an efficient quadrature with a controlled precision. We assume the data to be given on a hexahedral grid. Each voxel is then processed independently. Within the voxel, trilinear interpolation is used. This gives rise to a cubic polynomial of the density along the ray. The transfer function is given as a piecewise linear function. Applying it on the density along the ray gives rise to a piecewise cubic function. We propose a ray splitting algorithm that can analytically compute this piecewise function. The control points of the transfer function define isosurfaces of the density. In a first step, we analytically solve for these isosurfaces. These intersections define the segments of the resulting function. Then, per interval between two isosurfaces, the associated segment of the transfer function is identified, and the density and transfer function is combined to give rise to a cubic function at the current segment. This step is repeated for all segments. With this, no peaks can be missed. Each segment of the ray is integrated individually. Per segment, the color and absorption are cubic polynomials. This allows to simplify the volume rendering integral. The inner integral can be solved analytically, giving rise to a polynomial of degree 4. The outer integral is then solved via Simpson quadrature with analytic error bounds. In the first test, we evaluate the per pixel errors of constant stepping. We use a synthetic dataset of an expanding and shrinking tube at a resolution of 256 to the cube as test case. As one can see, a large step size leads to massive artifacts. The errors can be measured, for example with RSC curves. These curves plot the allowed per pixel error to a baseline on the x-axis and the number of pixels that fulfill this error bound on the y-axis. A higher value indicates less errors and more pixels are within that error bound. The vertical dashed line indicates an error of 1 over 256, or where differences would be larger than 1 bit on an 8-bit display. Now the step size is decreased. The error is reduced, but the rendering times becomes very large. Note that the time is in logarithmic scale. Ray splitting allows for more accurate rendering in less time. Now we repeat the experiment with a sharper transfer function. The convergence of constant stepping is lower and the errors are generally larger. Again, ray splitting allows for more accurate rendering in less time. Convergence rates can also be compared in a different way, shown on the thorax dataset of resolution 512 x 512 x 286. This dataset is interesting as it highlights the advantages of DVR. All peaks in the transfer function have the same small width. For the lung and the bones, this leads to clearly separated surfaces. But the stomach area remains smooth, highlighting the high uncertainty and variation in densities there. Now the step size is halved until we get a noise-free image. This means until the output does not change more than an 8-bit display. At the same output precision of 1 bit, ray splitting requires a magnitude less time to render. The same results hold for all tested datasets, for example a CT scan of a stag beetle or the ejecta dataset, a supernova simulation. For further details and timings, we refer to the paper. The proposed ray splitting algorithm is general enough to allow for several extensions. Krauss proposed in 2005 scale-invariant volume rendering, an alternative to the standard volume rendering, where the integral is evaluated over the data domain instead of the spatial domain. The assumption for computing this variant, however, is that the density is monotone per ray segment. This is quickly violated with constant stepping. With the proposed ray splitting algorithm, we have an explicit expression for the density along the ray. Therefore, we can simply solve for extrema of the density, that is, the roots of the first derivative, a quadratic polynomial. Splitting the ray there gives perfectly monotone segments. This allows us to render the scale-invariant integral without artifacts. Furthermore, the emission term can be extended with additional effects like Phong shading. Analytical error bounds are no longer possible, but one can still benefit from the splitting at the control points of the transfer function and analytical solutions for the absorption. Last, the ray splitting algorithm can also be used for multiple semi-transparent isosurfaces. By combining transparent isosurfaces and volumetric effects around the isosurfaces, hybrid visualizations can be achieved. We imagine that this could be used, for example, to visualize local density distributions around the isosurfaces. The effect becomes especially visible when a clip plane is introduced. Here is again the transparent isosurfaces with and without the volumetric envelope. Thank you for your attention.